Hello, we are Team 9, and this is our request for proposal for the Global Emergency Autonomous Response System, or GEARS for short. In this presentation, we will go over the project objectives, the design process, the cultural and ethical considerations for the project's physical design and navigational algorithm, possible areas for improvement, and recommendations for the future. The purpose of the GEARS project is to create an autonomous system that can transport cargo through an unknown path and deliver it to any recipient internationally. There are 6 main parts of this project. First, we have to develop a prototype for a robot that can perform a precise navigation through damaged areas represented by a maze. It has to transport a designed cargo container through that unknown territory to a community on the other side. While it does that, it has to characterize and avoid hazardous locations using sensors and magnets. While it does that, it has to create and transmit a map of the path that it takes through the environment. It has to indicate the contents of the cargo using a method that's not necessarily tied to any specific language or culture, and it has to communicate its delivery to the community recipients in a very non-hostile manner. As shown by the work breakdown structure on the side of the screen, there were several different priorities when developing the GEARS system. First was the design process, which involved planning and assigning roles. Then there was the mechanical design, which involved creating the physical prototype. The programming priority, which involved creating algorithms for movement, sensor identification, and other necessary components of the algorithm. There was also the collection of physical documentation to be utilized in the final report and presentation. Several different models were made in order to ensure that roles were assigned correctly and that a solid plan had been developed, including creating a theoretical Gantt chart for the project, as well as assigning roles. Jessica was the meeting coordinator, Nick was the encourager, Bobby was timekeeper, Jen was the recorder. Jessica was in charge of mechanics, 3D modeling, Nick was in charge of mechanics as well, Bobby was in charge of programming, Jen was in charge of documentation, and all of us were in charge of providing deliverables relating to the specific components.
Due to the nature of the project objectives, the GEARS will have to interact with different cultures, which could lead to cultural and ethical barriers. Not all human populations view technology, symbols, or outside aid in the same light, so the GEARS must be non-threatening aesthetically and independent of any language, spoken or written, as well as avoiding the vast array of ethical issues of aiding in certain disasters. Some cultural issues considered were the GEARS appearance and the label for the cargo container, and some ethical issues considered were the impact on the native culture and the type of disaster. Regarding cultural interactions, the GEARS would be designed with one of 4 cargo labels. The labels were designed to communicate visually without the aid of language. Starting with the label for food and water, the blue drop represents water. A tear-shaped drop is seen in many cultures as a positive symbol and usually that of water. Continually, the wheat in the label represents food, as almost every part of the world has some form of grain that resembles wheat. The hand at the bottom of the picture is symbolic of the hand of God in Western culture, or as a sign of peace in Buddhism. This hand is found in every label, and because it is a universal sign of peace. Another feature in all 4 labels is a solid black border to make it look clean and professional. The second label would be the label of a fuel source. Since every culture does not have fuels like oil or natural gas, wood is more universally seen as a fuel source. Wood is used in the symbol because most people who see the image of wood will at least equate it to a heat source. The gas can next to the stack of logs is to convey to the more industrial areas that the contents of the container are some sort of fuel. While many third world countries may not recognize the symbol, it would help convey to first world nations this idea. The third label would be the label for medical aid. Mankind has been using some form of bandages since ancient Egypt, where they used honey, grease, and lint to wrap open wounds. A similar practice has been seen in ancient India and Greece. The rationale behind this design is that virtually every culture has some type of way to stop bleeding, which means covering the wound in some material which justified the bandaged open hand. The fourth label would be the label for shelter. The label uses the image of a tent, as many indigenous people of Northern Europe, Africa, and Asia still use these kind of tent structures. While this form of shelter is not used in many places today, tents are still widely recognizable. In order to provide quantitative evidence for the container labels, surveys were used as a way to collect data from outside sources on their effectiveness. Before the survey was created, metrics had to be put in place to ensure that the symbols would work for a variety of people. The percentage of answers that had to be related to the label was 75% in order to become the final label. This percentage was set based on the idea that the survey would be open-ended, so each participant could fill in their own answer, allowing for a more accurate view of how the labels were interpreted. For the first label, the number of responses that related to food and water was only 73%, meaning the label produced did not meet the metric for acceptance. However, upon investigation, there were multiple responses related to agriculture, which were not counted in the total number of food and water-related responses. Because agriculture is very closely related to food and water and is an important aspect of almost every culture, this discrepancy was overlooked and the label was accepted. For the other three labels, the percentage of related answers was at or above 75%, meaning that all four labels were accepted as the final iteration.
The work on the physical design of the gears started first by identifying all necessary customer needs, and then using those customer needs to develop quantifiable engineering specifications that could be used throughout the design process. After that list of engineering specifications was developed, a functional block diagram could then be created to allow the different subsystems to be laid out and organized. Now, breaking apart the various subsystems, there are four primary aspects that had to be developed on the gears, which include the drivetrain motion components, the sensor arrays that would allow it to detect the environment around it, the cargo deployment for deploying the cargo container, and then a delivery completion signal that would allow people to understand and know when the cargo was delivered and when it was safe to grab it. First, the drivetrain motion. Two main options were looked at, either tank treads or having two wheels in the front with a pivoting wheel in the back. Now, through the use of prototypes and evaluating it with the code, it was determined that the track provided the most optimal solution, as it could have a zero turn radius. Even though the wheels had a very tight turn radius, it wasn't quite enough, and they also had more precision in the wheels. The drivetrain itself is very compact, and we shot for having it about a little less than half the width of the corridors it would have to pass through, which is about 10 centimeters. Moving on to the sensor arrays, there's three primary types of sensors that would be required to allow the gears to navigate. Wall-finding sensors, or ultrasonic sensors, IR detection sensors, then a magnetic detection sensor, or an IMU. Wall-finding sensors could be most optimally placed with one facing the front and one facing left, with one facing right. While a code could be developed to allow it to navigate a maze with only a forward and right-facing sensor, having the extra sensor allows more flexibility while coding, while also helping with the mapping algorithm. For IR detection, a simple array of two sensors could be placed in the front, allowing it to detect as it's getting closer to an IR hazard, and giving it plenty of time to turn around, make note of that IR hazard, put it on the map, and then turn around before it reaches within the unsafe radius. And finally, the magnetic detection sensor. This has a bit more flexibility in the IR, as it can detect magnetic fields from multiple axes, so it could be placed near the center of the macro, and also integrated with the code, so as it approaches the magnetic hazard, it would have plenty of time to turn around. Moving on to cargo deployment, it's kind of in the lower section of the functional block diagram. This would be critical as it would need to be reliable and securely hold the cargo as the gears is moving. The best method we developed was having a ramp that could deploy down, that acted as a platform, almost like a dump truck, so it could hold the cargo while it was navigating, and then act as a ramp so the cargo could safely slide down to the ground. Also integrated with this was a delivery completion signal, which is a flag attached to the motor of this cargo deployment method. This allowed a flag, almost like a mailbox, to go upwards, alerting people that it was now safe to grab the cargo after the cargo had been deployed. Now, all of these decisions were not made without research and using prototypes, and part of what helped with that process was decision matrices, where different systems could be tried out and given different criteria and weights, and totals could be added up to allow us to select the most optimal method. So here's two examples of some of them that were used. The one to the left, we have the weight of four-wheel drive, turntable, and tank categories for describing the best way to have it move. And as you see, the turntable that we initially talked about in the previous slide did have the most points, but through further testing, it was proven to be unreliable with navigation. So that's why we went with the second best one, which was the tank. Also for the wheels, which is the one to the right, this was for testing the four-wheel drive and turntable methods. As you see, the traction and width and height being very important as the drivetrain was compact, were also used to develop the best wheel size when we were testing those methods.
The prototype cargo container was 3D modeled in SolidWorks. It features one lid, one base, and 4 identical bolts. The base is a 40 by 40 by 45 millimeter cubed, hollowed out box that is able to contain the 200 grams of required cargo. The lid snugly fits over the top, and the holes on the sides of the lid and the box line up. When they line up, the bolts go through the sides, keeping the two together and preventing the cargo from opening.
In general, the logic of the gear's navigation can be thought of as the combination of the core functions and 3 distinct algorithms: self-centering, path choice, and mapping. And as the code is implemented, those 3 algorithms will be nested in that order. As you can see on the right, we have a brief system chart of the general run loop, with self-centering being the first function called. But first, the core functions. Any autonomous navigation device will always need 2 functions, a move function and a rotate function. For Team 9, these functions embody themselves as a function called drive and 2 functions called turn left 90 and turn right 90. The drive function is very straightforward, no pun intended. The drive function would simply turn on both the left and right motors at a designated rotational speed to achieve a desired linear speed. Also, it is important to note that the drive function is not a null function, but instead returns a floating point value. The distance traveled during the time the function was ran. While this time and thus the distance will be small, it's the small incremental distance that will be constantly updating the current location variable, which will be used later in the mapping function. Additionally, the gears will incorporate 2 turning functions. Both turn left 90 and turn right 90 will do exactly as their names describe by turning one motor forwards and the other backwards, achieving a perfect point turn. Both turn functions will also update a direction variable. Direction will start at 0 when it first enters a maze. Every turn to the right will increment direction by 1, and every turn to the left will decrement direction by 1. To correctly access direction, the modulus function will be used to ensure direction always lies between 0 and 4. Or 0 and 3, rather. The self-centering function is rather simple. The corridors are all of a constant width, and the gears is of a constant width. As explained by Nick, both side ultrasonic sensors are symmetric about the center of the gears, so the distance between the wall and the sensor should always remain constant. In our case, we will use 10 centimeters as a perfectly centered distance. Our program would then use bang-bang feedback control algorithm, so that if, for example, the left ultrasonic sensor detected less than half of the perfect distance, it would make a slight turn to the right by reducing the right wheel to 75% until we were within the 5 centimeter threshold again. Bang Bang was chosen over other more refined approaches with fair reasons. Both the integral and proportional controls were too slow if the gears were to be more than ever mildly off course, and the derivative control was wildly out of control and would routinely throw the gears robot into a wall. A flowchart for the Bang Bang control can be seen on the right. The next and most essential function is the pathfinder, or rather the path decider algorithm. The gears will get the values for the distance to its left, right, and in front. If it deems there is a path to the left, if the ultrasonic sensor reads more than the width of a corridor, it will turn left. If the left is unavailable, it will go straight. If straight is not an option, it will turn right. And if none of those are an option, it will turn around. Given that the maze is simple in structure, by following this left-hand rule, this is 100% effective and will always work. To the right, we show a diagram of each of the 4 circumstances previously described. Finally, we have our mapping function. Fortunately, the core functions and previous algorithms allow for a map to be easily formed. It would take 3 inputs: a direction, location, and a list of boxes. After every call of the function, the distance output is either added or subtracted to either the x or y position of the location array. The location is then put through a box checker algorithm. The box checker algorithm checks to see if a point passed exists in a box in the box list. The box lists start with the bottom right box as seen on the screen, defined as 0 to 40 in the vertical direction and negative 20 to 20 in the horizontal direction. If the point is not in the box, a new box is added. This is continued until the gears exited the maze. To the right is a theoretical visualization of the mapping function's data.
In conclusion, the gear system has fully been explored through the cultural and ethical considerations, the physical design, the navigation algorithm, and the cargo container. Our design has many positive attributes, some of which being that it is very culturally and ethical aware, and that we have a preliminary prototype which would greatly aid in future development. However, we were unable to test this prototype after the algorithm changes and container changes, and the range of people surveyed were not as culturally diverse as we wanted. We believe our prototype is a very good starting point for the gear system and that it could be easily modified into a working system. Thank you for your consideration.